I should try now to start recording again. It is still December the 7th, and now we are not in the morning, we are in the afternoon, and we are considering the second of two papers by Bengt Halstead and Medinuri. No, this one we do. This one, yeah, okay. Should I share it? Hope it works. And so let us go back. This one I have posted here. This recall the lecture of this morning. It should be on YouTube over there. And so we will go back again to a paper by Bengt Halstead and Medinuri. We will try to find them in the Calphad journal. In the Calphad journal, I think it is a recent issue. That's the one published in December, probably. Blah, 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 blah. And so let us check if I'm finding it. This one I would like also to discuss, this one by Axel van der Walle, and also the other one, the viscosity database, but I need some time, not now. Blah, 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 blah. And this one as well, this, I mean. Okay, I was a little bit disappointed. So this one, and this is the journal, so university e-library version. And if you don't have it, you should get somewhere else. The Social Science Research Network. Is it on the ResearchGate as well? Probably yes. So it is on ResearchGate, but is not necessarily available, while here on the Social Science Research Network, SSRN, it is available. So we have two versions, one open here, and one, I don't believe it is open, this one, on the Calphad journal, which is the basic journal of this. It is not the only one. So we would download the database somewhere. Let us put it here. And we need then to get where the downloaded material is, which likely should be there. But we will have this database. So you remember that databases, they end with the TDB. So this is MPEA line 05. We can have a look. It is a database containing aluminum, cobalt, chromium, iron, manganese, nickel, vanadium, and carbon. So this is a multi-component database for high entropy alloys. So multi-component phases, which have been very well introduced in the lecture by Professor Cantor, that we have recorded in Professor Badesha 123 YouTube channel. I've told you before that it is available. But for this database, we need some special modeling tool, which are included in Thermocalc and are currently not included in Pandat. So I have modified it, and I think I should export somewhere. Put it in a directory, which could be the directory, the remote directory of our course. And in one, I would copy this file in two ways. This one, TDB, and this one, I will give it the extension txt, because when you will be able, if you would like to download it, it will be easy to get this text file, and for most of the browsers, not possible to download this extension. But basically, it is totally the same file. So the name is different, the extension is different, but the file is totally the same, with the total number of bytes equal one to the other. Well, once we have downloaded, blah, 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 I think I would open now Pandat. I think the last full version that I have available is probably Pandat 2021. Let us hope it is working. So my lines, you need a dongle, you need to buy it. And so let us create a new workspace like we have done previously, database. Let us load our database, which could be here. I think we will have some wordings. And we will select the 8 components altogether. You cannot select all of them because you have the version limited to 3 components. But as long as I will do some work here, it would be possible to do some work and to produce a workspace and to compress this workspace, and then you can download the workspace. So I would like to do all binary phase diagrams, but because I'm fond of steels and iron-based alloys, I would just use one component on the left and all the other on the right. I think we still will have in molar fraction. Let us see if I am correct. So this way, we are using an adapted database. It was not very difficult to adapt. It was just cutting a specific phase that needed some permutation in the lattice. And I'm sure that Medinori, that has been doing the work, is able to do with Thermocalc this one operation. We are just at a very introductory level, so I think we are already satisfied by doing those binary phase diagrams for a while. This is iron aluminum. I think we are still in moles. This is good because if you want to compare results here with those two papers, it's good that we have moles in our figures. Of course, being an engineer myself, I tend to use weight percent, but for many studies, it's better to use molar fractions. I was wondering if you would like, I hope so, to see a couple of phase diagrams with something like fixed level of something in 2 graphs. So we have iron chromium. You know that for stainless steels, iron chromium is the basis because you need at least 11% in weight to have a stainless steel. You have been studying it some previous course. So manganese, nickel. So now you notice what we can do doing binary, all binary phase diagram with the phase diagram common, but fixing one. And so the one fixed here is the one that is on the left, which is iron. And we have basically made 1, 2, 3, 4, 5, 6, 7, yes, 7 phase diagrams. Well, what we can do now, I would like to, well, the iron carbon phase diagram is a little way not really explore for high carbon compositions, but this will be another. But I am rather of the opinion that I could show you something more for the iron chromium and the iron nickel phase diagram. So you remember that we can select, we can do a binary phase diagram. We should select components. No, we should select components in the database. So I want to select just iron and nickel and nothing more. And, you know, I am interested in this course to have some consideration in the solidification because I think it is one nice modeling game. And so we will add contour lines. We will add the contour lines. How about adding contour lines with the fixed composition? And yeah, so this one. So how much phase it's in the liquid? So we've been using previously in the previous lecture. So in the contour lines, in the phase diagram, we will see the phase flexion. Let us do it, and then it will be simple to understand. I would do this for iron nickel. I should have done it before for iron chromium to respect some sort of alphabetical index. Never mind. No, I would not answer the phone now. I want to finish this one. So we can see those contour lines, not very efficient actually. And well, I would try to do again a binary phase diagram, selecting other elements as well. Select components. Now I would select iron and chromium. And please notice that if you want to do a binary phase diagram using iron on the left, you should work in such a way. So 0 here and 1 here, 0 here and 1 here, 1 here and 0 here corresponding to the X. So Y, origin X, extra outputs, no, contour lines, yes, liquid phase, yes. Contour, yeah. We have selected liquid phase, but we could have been selecting other phases as well. I'm not using labels for the moment. I told you we can add labels. So here is nicer, I think. Then we should enlarge the graph. How can we enlarge the graph? We go into this left window, and then I would say that we want to work from 180, a little bit less, up to 2200. And so let us check if it is. Okay, little bit less. And no, I prefer 2200. Okay, not too bad, not too bad. So these are the conditions that we have been producing. So again, like we have done before, what if, I would also do it here. So in the range 850 here, which is correct, up to 1700. Yeah, but it is still compressed. And still too much compressed. Not so satisfying because it is more difficult to set. You should press F2 and then click with the mouse. Let us see if it is true. And then you can add, in this case, labels. So remember that we've been using, so this is fully liquid because it is the liquid of temperature. So 0.8, 0.6, 0.4, 0.2, and then all solid. And then this is the mixed area, BCCA2 plus liquid, okay? Well, for the moment, I would just try to get, if I can, copy some other databases. So today, I have noticed that my colleague Aurélie Jacob, she's been publishing a new paper on the, would say, multi-components iron-based alloys useful for calculation, thermodynamic calculations on bainite, Aurélie Jacob. And this is a nice work, which has been published yesterday. And so, we've been working with my students for a while, and also Aurélie, she has been here some months ago in May. But the important thing is that she's been modeling according to the model proposed by Professor Badesha by night. And what I want to get is the Matcalc open databases, which are extremely useful. So already she is from the Technical University of Vienna in Austria, and they have produced a specific software by Professor Kozetnik, which is called Matcalc, and Matcalc is over there, www.matcalc.it. Okay, so this is Matcalc, and of course you can download it, use it, and also it's free up to 3 components as well. But I am not very good in using it. So what I can use their open databases. So I would get this by night database, which has been published this year in March. Let us download somewhere in my PC, in lecture 1, here. And possibly we should save with 2 different links. So this one, and let us see if it works. Now, file, database load. Let us select the same component. Let us be lucky that aluminum, carbon, cobalt, chromium, nickel, manganese. What else? There was vanadium. Vanadium. One should be 7 components, including iron. So they are 8. Again, we can do these all binary phase diagrams based on iron. And we can compare the 2 databases, the one by Orly Jacob and the Matcalc group, and the one by Bengt Halstedt and Mehdi Nouri by RWTH Aachen and by Professor Bengt Halstedt. The one, this last one, is made on purpose for by night calculation and basically for steels. So one would expect that it would work in the typical steel ranges, which have always something about iron, carbon, and then other components, to speak very, very superficially. And then I would like to see how the 2 data sets overlap or not. I don't know the answer, but as I've been showing to you, copy data and paste data, one may show to you. I think I have 2 or 3 minutes more, then for some reasons I have to leave this recording. Okay, so let us copy data here with this second paste data. Okay, this is indeed different. So let us copy iron, carbon, forget about this. These are artifacts, but nevertheless, we will copy abruptly the data from this first database to the second one. The situation seems pretty identical. So we will copy those data there. And again, we will have something different as well. And again, let us go on the first iron chromium there. Suppose to find something the same. Not really. We have some magnetic modeling interaction from one field to the other. Iron nickel, copy data, and paste data. Yeah, different again. Iron manganese. Copy data and paste data as well. The situation is still different. Then last one, I think, for our data set, copy data, vanadium there, copy data, and paste data. This seems the same. Okay, so for the moment, save current file as workspace as we are in lecture 1, and I would use lecture 1, lecture 01, MPEA. Yes. Let us close everything. Let us say that we have a few seconds to compress. So the database would be here, not here, but the workspace will be there, and I would now compress it. And then it should be zipped, and from where it is zipped, I would put it there. And I think you would find it because we have an index. And so I would also add this one and this one, that in any case you can download directly from the Matcalc site. I think that's pretty all. So I should try to interrupt recording or anything that we are doing. Yeah, there. Half an hour is pretty enough for, and I should say bye to you and see you next lecture. Stop recording.